Okay, so we have the problems on heat of formation, heat of combustion, and many other reactions. But for this week, you have the numerical based problems on the heat of formation and heat of combustion. That is once again heat of reaction also, and first law of thermodynamics. And here some topic you have what bomb calorimeter. Okay, bomb calorimeter, and for which you may not have proper stuff in the book, but listen, it is need not to learn much about the bomb calorimeter, because it's not big what part of this chemistry. Here why that bomb calorimeter came, the reason is, okay, the reason for the this bomb calorimeter topic is that here the combustion means the burning of substance in free supply of air, free supply of air is carried in a bomb calorimeter. Okay, bomb calorimeter. So see beta, as in the bomb calorimeter, the volume is constant. Volume is constant. So remember the heat of combustion, as we know that always negative value, because the combustion reactions are exothermic in nature. Because everyone knows, manandariki telusu, combustion of coke, combustion of fuels, okay, combustion of LPG or whatever it is, wood, charcoal, they all produces energy, and we use that energy for the cooking purpose, or maybe running vehicles, steamers, etc., rockets, aeroplanes, etc. So all these the fuels are burnt in what, closed engine. So the when it is closed engine, the container is there. So it must be what, non-expandable, non-contractible. Means the fuels or hydrocarbons which are in the fuels, they have to burn at a constant volume, because the container must be what, non-expandable. Because you know what happens, the gas which is taken in the engine, if it is expanding, what happens, it will, okay, it will burst. Okay, the engine or the tank will burst. So therefore the combustion reactions takes place at a constant volume. Please tell me any physical process or chemical process which occurs at a constant volume. So what type of process it is, which is carried in engines or calorimeters, bomb calorimeters? Please tell me what is that type of process called? Because in the beginning I gave some process like reversible, irreversible, cyclic process, and next constant temperature, constant pressure, constant heat, like that, constant volume. Please anybody can tell me any process or chemical change reaction which takes place at constant volume. What is that, what is that process? Please please tell me anyone. Isochoric process. What is that called? Isochoric. Okay, isochoric process which takes place. So the combustions are isochoric process, and this is done in what, bomb calorimeter. So listen here, what is this bomb calorimeter? First of all, you will have a bomb in that. Okay, don't think it is a bomb explosive. Okay, bomb means a simple copper bowl will be there. ఒక కాపర్ గిన్నె ఉంటుంది, చిన్న గిన్నె. Because how you cook the food or anything in the containers, can you listen me? Okay, how we cook the food or any something, okay, in the containers, గిన్నెల్లో మనము బౌల్స్ లో ఎలాగైతే మనము కుక్ చేస్తామో. So when in bomb calorimeter, okay, in bomb calorimeter, when the fuel is or hydrocarbons are burnt, when hydrocarbons are burnt, so you want some container, you want some container. So in this, okay, so in a bomb calorimeter you will have one copper bowl. Okay, you will have one copper bowl. So this is what I have drawn here, some red color bowl. Okay, this is a copper bowl, and we know that this copper material itself is a matter. Yes or not? Itself is a chemical substance. Copper is a metal element. Is that clear? So this every substance, every matter, every system will have its heat capacity. Yes or not? Will have its heat capacity. I hope you know the heat capacity. The temperature required to raise, okay, raise to 1 degree Celsius or 1 Kelvin. Okay, so what is that? The heat required to increase the system temperature to 1 degree Celsius or 1 Kelvin. Okay, at given conditions, per gram of substance is called as heat capacity. So like that, this copper bowl also will have some heat capacity. Okay, heat capacity. Okay, this will have some heat capacity. So when in this container the hydrocarbons or coke, okay, take hydrocarbon fuels, please be quiet all of you. Okay, if a coke and a boggu kani, hydrocarbons kani, fuels kani, మనం తీసుకొని వాటిని ఫ్రీ సప్లై ఎయిర్ లో మండించినప్పుడు ఏమవుతుంది? ద బర్న్. ఓకే, ద కార్బన్ చేంజెస్ టు CO2. హైడ్రోకార్బన్స్, ఓకే, if you take any hydrocarbon, alkane, alkene, alkyne, whatever hydrocarbon is there, so from the hydrocarbons all the carbon changes to CO2, all the hydrogen changes to H2O. And what I said that all the combustion reactions are exothermic in nature. Exothermic in nature. So see here, when you burn the hydrocarbons or the carbon in this bowl, so what happens? Heat is released. Yes or not, children? Tell me, send me the response in chat box. It will, okay, release the heat or not? Yes, of course it releases. So you know that what is temperature? What is temperature, beta? What is temperature? Tell me, dear. What is temperature? The temperature is the measure of heat. The temperature is the measure of heat. Antena? Measure of heat or measure of coldness. How much heat, hotness is there? How much of coldness is there? That is called temperature. So see here, this copper bowl is immersed in the water. It is immersed in the water. So for this water, you have to first check its temperature. You have to check its temperature. So previously, the temperature of this water will be T1 degree Celsius. T1 degree Celsius. Okay. Now in the copper bowl is having water heat capacity Q. So here the heat capacity is for both water and copper bowl also. Okay, means how much heat it can accept or absorb. Okay, the total system. And next, when you burn the hydrocarbons in this copper bowl, you first initially measure the temperature of that water. Okay, water in which the copper ball is placed. Okay, copper ball is placed. And next here, after burning this hydrocarbons or coke, what happens? Heat is released, and that heat is called as heat of combustion. Okay, heat of combustion. So what is combustion? A type of reaction, and in which we are discussing heat changes. So heat change is given by delta H. So for combustion, we may write delta H or delta E. Actually, we should write delta E, but generally we write delta H. So I'll write here C. Okay, delta HC. So here the hydrocarbons are burnt in the copper ball, which is called as bomb. Okay, which is called as a bomb, which is placed in the water. And for that water, we have to first measure the temperature in the Celsius. Then after burning, after burning the fuel, what happens? Some heat is released. So After burning, some heat is released, and that heat is what? Absorbed by this copper ball, then water. And what happens? The temperature of water increases from T1 to T2 degree Celsius. Is that clear? T1 to T2 degree Celsius. So here you have to calculate the rise in temperature. How much the temperature is increased? Because before combustion, the temperature of this water inside the bomb calorimeter is less. After combustion, from the fuel or hydrocarbon or the coke, heat is released. So that heat energy is absorbed by water and copper ball. So automatically what happens? The temperature rises. It will rise from T1 to T2 degree Celsius. Could you get me? So here the T2 minus T1. Okay, T2 minus T1 will be what, beta? I want answer. Will be what? Difference in temperature. Difference in temperature. So this is given as theta. Okay. And generally the reaction is exothermic. So what is this? Difference will be increase in temperature. Is that clear? Increase in temperature, or you can say it is rise in temperature. It is given by delta. Sorry, it is given by theta. Okay. So the difference between this T2 temperature and T1. So I'll change here T2 and this is T1. Okay. So T2 is after combustion, T1 is before combustion. The difference between them is theta, which is increase in temperature in degrees Celsius. Okay. And next here see this bomb calorimeter, this container, bomb container, which is immersed in the water. Okay, immersed in it water. It is placed safely in a wooden box. In a wooden box. So this square box which I have shown, that is what wooden box. It is a wooden box. Okay, and around this the water tub which is kept here. Around this we have to use one insulating material like cotton. Okay, cotton or the fox fur. Fox and telsa. What is fox? Fox nakka. Okay, or sheep gorre. Okay, so we know that the wool is obtained from sheep's. So sheep wool or fox fur or wool is kept, which are insulating substances. Means they will not allow the transfer of heat from water to outside. Okay, water to outside. So here and during this combustion you may mix also. So therefore a stirrer will be there. So what is happening here in this when you observing the heat of combustion, so it will bring the change in the temperature of the system. So see here I'll write here heat capacity of this copper ball or system is Q, then into the rise in temperature. The rise in temperature is theta into then molecular weight. The molecular weight, because the hydrocarbon or any substance which is taken, definitely it will have some molecular weight. So into molecular weight of that chemical substance which is subjected to burning or combustion, divided by you have to take the substance in certain weight divided by mass of that substance taken. Means for example, please tell me better. Please tell me what is the benzoic acid formula? C6H5 phenyl COOH. C6H5 phenyl. To the benzene ring, if you attach the COOH, to the benzene ring, if you attach the COOH, so it will have 7 carbons. C6H5 COH. So C7H6O2. The benzoic acid molecular formula is 122. So this benzoic acid some amount is taken. Say 4 grams of benzoic acid is burnt. So the small m is the weight of benzoic acid which is burnt in bomb calorimeter, and m is molecular weight of bomb calorimeter, and this Q is heat capacity of this system inside. What is that? Copper ball along with the water. And this theta is rise in temperature. Rise in temperature. So when you use this formula, we can calculate the heat of combustion of reactions. Okay, heat of combustion of reactions, where combustion means what? Where combustion means what? When a chemical element or any chemical substance is burnt completely in free supply of air. In such a case, where the elements of that compound convert into its highest oxidation state. Okay, so this is. And note one more thing: the heat of formations can be calculated from heat of combustion by changing their sign. So you will be having some interesting and some confusing problems on them. So yesterday I have sent you some problems, solved problems, and today I will send you some more. Okay, so here from the combustion heats and the respective reactions on addition or subtraction, we have to calculate the heat of formation. Okay, it is called chemistry because chemistry will not be completed without writing equations. So here you have to convert the heat of combustions into heat of formation of substances. It will be very interesting and means illuminating numericals we are going to solve. Okay, so here see, as I told in combustion reactions, the element has to convert into its highest oxidation state. So remember when the coke means carbon. See beta here, coke. Okay, coke. Yesterday we discussed the coke will exist as diamond and graphite. See here, the coke will exist as carbon will exist as diamond and graphite. So please tell me, between the diamond and graphite, which is standard state? Diamond or graphite? Yes, beta. Between the diamond and graphite, which is a standard state? I want answer. If it is diamond, send me D. If it is graphite, capital G. Hello. Response, please. Are you sleeping? Graphite. Thank you, Sheikh Junaiddin. Okay. So see here. So if you burn the diamond in free supply of air to CO2, it is called just heat of reaction. It's called a heat of a reaction. But if you burn the graphite to CO2 gas in free supply of air, it is called not only heat of reaction but standard heat of reaction. And note this point when I send this video. Read, okay. Listen this point. So listen what it is. When graphite is burnt in free supply of air to give CO2. So here CO2 is formed. And carbon is combustion. So here three types of reactions are there. One is, okay, the three types of reaction. One is reaction, carbon to CO2, formation of CO2, combustion of coke. So see here, when coke is burnt to CO2, okay, if we take graphite, so here the heat changes is called as heat of reaction, and CO2 is formed, so therefore called as heat of formation of CO2. FCO2 means what? Formation of CO2, and here delta H C, heat of combustion of coke. And since the graphite is the standard state, Graphite is the standard state of coke, okay, carbon element. Itself, these heat of reactions, these heat of reactions called as standard heat of reactions. So, standard heat of reaction, standard heat formation, standard heat of formation of CO2, standard combustion. Okay, standard combustion. So here see beta. Now one more thing to repeat that combustion means what? Combustion means what? Here see combustion means I told that it has to change. The element has to change into its highest oxidation state. Highest oxidation state. Please tell me what is the group number of carbon element? Hello, I want answer. I want response. What is the group number of carbon? As I hope you know that carbon atomic number is 6. It's not group number 6. The atomic number is 6 beta. Okay, 14th group. Okay, thank you Uma Venkata Sai Gaud. Okay, so what is that? Atomic number is 6, group number is 14. That is 4th A. As it is having the 1s2, 2s2, 2p2 configuration where n equal to 2. The outermost shell contain 4 electron. So to get octet, how many more required? 4 electron. So it can lose these 4 electrons, then show plus 4. It can gain 4 electron, then show minus 4. So obviously we know that plus 4 is the highest oxidation state. Highest oxidation state of carbon is plus 4. So in CO2, the carbon will be, in CO2, the carbon is plus 4. Okay. So if the coke, okay, when the carbon, okay, whether it is diamond or it is a graphite, is burnt in free supply of air, okay, is burnt in free supply of air. But if it is giving carbon monoxide, if it is giving the carbon monoxide, so I'll balance this, half O2 will be equal to 1 oxygen atom. So here this graphite is burnt in oxygen air, but giving what? Carbon monoxide. Carbon monoxide. This is not combustion. This reaction is not combustion because in carbon monoxide, the carbon the carbon oxidation state is not plus 4. Is not plus 4. It is not highest oxidation state of that element. It is what? Plus 2. It is plus 2. So means it is not in highest oxidation state. It is not combustion. Just oxidation. Just oxidation. Okay. So the formation of CO2 from coke is combustion, where CO is just oxidation. So this must be clear. Okay. And next, okay. So as you all know that the heat of combustion of graphite to CO2 in a free supply of air is delta H. It is exothermic and this is found to be 393.5 kilojoules. Okay. And this is having what? Negative sign. So exothermic reaction, and since combustion, so combustion of this 1 okay, 1, that is 6 grams of coke, sorry, 12 grams of coke is 393.5 kilojoules, or formation of 1 mole of CO2, formation of 1 mole of CO2, okay, formation of 1 mole of CO2 from its elements is minus 393.5 kilojoules. Okay. And next, when you write the heat of combustions, okay, or the equations, the balanced equations for any hydrocarbons, so simple, remember, you are going to write the balanced equation for one molecule of hydrocarbon. So what is 1 molecule of hydrocarbon? 1 mole. Okay, 1 mole. So see beta here. See this reaction. See this reaction. The first is graphite. It is already discussed. So here see, here C2H6 is what? Ethane. Okay, C2H6 ethane. Now it is burnt in oxygen O2. So here when you write combustion reaction, remember always the hydrocarbon taken is 1 mole. Is taken 1 mole or 1 molecule. Take the 1 molecule of hydrocarbon. 1 molecule of hydrocarbon and balance the reaction with the required oxygen. So note here all the carbons changes to CO2. So C2H6 in ethane. So therefore 2 carbon dioxide. H6 3. So 6 hydrogens means 3H2O. So how much of oxygen required here? 3.5. 7 by 2. Like that here I have wrote for butane gas. So butane formula C4H9. C4H9. So here it is 1 molecule or say it is 1 mole. Okay, take the 1 mole of hydrocarbon, then write its balanced chemical equation. And we know that the balanced chemical equation means where the number of atoms of all the reactants and all the products are balanced, which is called as stoichiometric equation. Okay, then in this stoichiometric equation, if you put the physical appearance, the physical states of all the reactants and all the products along with the heat changes, that is delta H, whether positive or negative. So obviously we know that the combustion reactions are exothermic. So for this will be delta H is negative. So if you mention the heat changes, okay, heat changes and the physical states of reactants and products in the balanced equation, that equation is called as thermochemical equation. Okay, so now see here, it is butane C4H10. Now it is oxygen required is 13.2. So butane contain 4 carbons. So all the 4 carbons converted to CO2 gas. CO2 gas. And 10 hydrogens, therefore 5H2O. Now next, here, please tell me. Now you are going to write the balanced combustion reaction. The balanced combustion reaction for the balanced combustion reaction for the benzene. Please tell me what is the formula of benzene, beta? What is the formula of benzene? Tell me all of you. Hello. What is the formula of benzene? Benzene. Benzene, whose IUPAC name is cyclohexa 1, 3, 5 triene. Okay. Okay. Its formula is C6H6. Okay. C6H6. Okay. Benzene is C6H6. So when this benzene, remember the benzene exists in liquid state. Okay. Benzene exists in a liquid state. For this, I'll help you. How? The benzene liquid is used in dry cleaning the clothes, silk clothes. Okay. So benzene standard state is liquid. So when benzene is burnt in air, so air is oxygen, which is gas. So what is that combustion reaction? All the carbons has to change into carbon dioxide. So 6O2, which is gas. And here, how many hydrogens in the benzene? 1 molecule of benzene, 6. Therefore, you get here 3H2O. And H2O, which is formed is a liquid. Which is formed is a liquid. Now, balance the oxygens. So, yeah, you are going to balance the equation for only 1 mole of benzene molecule. Okay, 1 mole or 1 molecule of benzene compound. Okay, now count how many oxygens required. 6 2s are 12. Then 3 2 here 3 only. That is 12 plus 3. How much? 15. Okay, 6 2s are 12. Then it is 3 here. Tell me how much you require. 15. So if I write here 15, how many oxygen will be there? 15 2s are 30. So therefore 15 by 2. 15 by 2 O2 molecules. And here it is what? Very interesting equation. Why? Because the benzene molecular weight, the benzene molecular weight, okay, the molecular weight, gram molecular weight of benzene is 78. Okay, the benzene molecular weight is 78 grams. And when 1 mole of benzene, when 1 mole of benzene is burnt in air, that is combustion. So luckily, it will be a shortcut to us to easy remember. So heat released is 780 kilojoules. 780 kilojoules. So like that. So based on the mole concept, in a simple like mole concept. So if you know the heat of a given weight, you can calculate weight. You can calculate the heat of combustion for its molecular weight. Okay, or molecular weight per molecular weight per mole is known. Then you can calculate by for weight given by crisscross method, simple mole concept. Mole concept. Okay. And next, one more thing I want to tell you here. So 78 grams per mole of benzene gives how much? 780 kilojoules of heat. Okay. Gives out therefore minus. And next, tell me simple. What will be the heat? Okay, heat of combustion released for 50 grams of benzene. 50 grams of benzene. 50 grams of benzene. Use common sense and tell me answer. Okay, 78 grams of 780. 50 grams of X crisscross. What do you get there? What do you get there? 500. Okay, you can do the calculation in the air. 78 grams gives 780. 50 grams X crisscross. 50 into 780 by 78. That is 78 and this 780 will be get cancelled. So 50 into 10 is 500. Okay, kilojoules. So this is what mole concept, which is always important in chemistry. Where you have seen this in stoichiometry, states of matter, okay, and in all the equilibrium thermodynamic calculations. You need this because the mole concept is father of all. Okay, to do the numericals. That's what the person who proposed the mole concept, Lavoisier, he is known as father of modern chemistry because for the calculation the mole concept makes it easier. Okay, and next when you calculate the heat of formation or heat of combustion, okay, heat of combustion, be little careful. Okay, now see, in a reaction there is a reaction. Okay, there is a reaction. I don't know your page number. Okay, take one problem. It is delta H for the reaction. Delta H for the reaction. A solved problem is there, and I send also it is. I already sent to you. Delta H for the reaction. That is F2 plus HCl. 2HCl. In the question itself, balanced equation is given. F2 plus 2HCl give rise to 2HF. 2HF plus Cl2. This reaction is given, and for this reaction, heat of reaction is given. What is that? For this reaction, delta H, heat of reaction given is minus 352. Minus 352. Minus 352.8 kilojoules. Okay. And next, and standard heat of formation of HF is, and given is what? Standard heat of formation. Delta H, heat of reaction. F, heat of formation. Then 0 power means standard heat of formation. For HF given is, what is that? Minus 268.3 kilojoules. Okay. And in the question asked is, calculate the standard heat of formation of HCl. Okay. Asked is standard heat of formation of HCl. The given value for HF. Asked to calculate for HCl. This you have to calculate. So here see, in this reaction, tell me beta, what is HCl? HCl is reactants and HF is a product. So generally heat of reaction is enthalpy of product minus enthalpy of reactants. Enthalpy of product minus enthalpy of reactant. So here we can write with respect to the product and reactant. So what is the here? What is the product beta HF? So therefore that is enthalpy of HF. Okay, minus enthalpy of HCl reactant. So here we consider for 1 mole, but in the reaction how many? 2 moles. Therefore 2 HF, 2 moles of HF enthalpy minus 2 moles of HCl enthalpy. Put their values and you will get. And what is asked here? Enthalpy. You are asked to calculate enthalpy of HCl. So this one you want. This one you want. So here we can write as here. So you can write this one as delta H for HF. Okay. ऐसा भी चलता है इलावा delta H because enthalpy changes of product and reactant. So that is delta H of HCl, which is for 2 moles equal to. So what it is? What it will become, beta? What it will become? Tell me. When you bring this, okay, when you bring this delta HF other side, delta HF other side. So this positive becomes a negative. So make it positive. So just here, see this is what could be the value? What could be the value? So just bring the HCl other side, minus become plus, and here 2 delta HF, then bring this delta H to this side, that is delta H, that is delta H. Okay. So now here totally the sign is changed. Put the values and you will get for 2 moles. You will get for 2 moles. Then divide by 2, that is 2 delta H HCl by 2 moles of HCl will give you heat of formation of 1 mole of HCl. So in this way you can do calculation. So check this calculation and I will send you some more calculations. Yes, answer is 91.9.